London, winter of 1660. The city was wrapped in mist and coal smoke, its narrow lanes glistening under the dim glow of lanterns. Inside a modest room at Gresham College, a candle trembled against the cold air, its light pooling over quills, glass flasks, and brass instruments. Around a wooden table sat a handful of men, scholars, artisans, philosophers, speaking in measured tones that carried both exhaustion and quiet wonder. One of them, his ink-stained hand resting on a notebook, murmured, "Let us no longer believe because we are told. Let us find out." The others exchanged glances. It was a simple statement, yet it would divide centuries. The scene could have passed unnoticed, a small gathering amid the hum of London's restless life, but in that fragile glow, something vast was taking shape. A new fire was being lit, not in the hearth, but in the human mind. The candle's flicker became a symbol of a greater awakening, the light of reason rising against the long shadow of tradition. This was the moment when humanity began to ask questions not in prayer but in proof, when men dared to believe that nature could be understood not through faith alone, but through observation. Europe in the 17th century was a continent scarred and uncertain. The 30 Years' War had ended only a decade earlier, leaving behind a trail of ruin that crossed borders and beliefs alike. Entire towns had been burned, nations divided, and faith itself had been weaponized. From the cathedrals of Germany to the fields of Bohemia, the old world order seemed exhausted. For generations, Europe had lived under the authority of Scripture and the wisdom of Aristotle, a universe that was ordered, finite, and explained through divine intention. The heavens moved in perfect circles because they were the dwelling of perfection. The earth lay at the center because it was the stage of salvation. Yet doubt had already begun to whisper. In Poland, a quiet canon named Nicholas Copernicus had proposed that the earth itself was not still, but in motion, a planet among planets circling the sun. In Germany, Johannes Kepler followed the mathematics to their inevitable conclusion. The orbits were not divine circles but ellipses, elegant and precise. In Italy, Galileo Galilei raised his telescope to the night sky and saw moons around Jupiter, craters on the moon, and the shifting phases of Venus. His discovery struck at the heart of belief, not to destroy faith, but to reveal that truth could be measured. It was a time when courage looked like curiosity. Scholars risked their reputations, sometimes their safety, to peer beyond the veil of custom. The world revealed by God was slowly giving way to the world discovered by man. The authority of revelation was being tested by the evidence of the senses. For the first time in history, knowledge no longer flowed downward from kings, priests, or ancient texts. It was drawn upward from observation, experiment, and reason. To imagine 17th century Europe is to picture a continent at the crossroads of faith and fact. Printing presses clattered in cities like Amsterdam and London, spreading not sermons, but ideas. Merchants carried not just goods, but knowledge, maps, measurements, instruments. The sea routes that brought spices and silk also carried telescopes, barometers, and microscopes. From these tools came a new worldview, one that saw nature not as a mystery to be feared, but as a system to be understood. England was particularly ready for this transformation. The turmoil of civil war had shaken the old hierarchies, and the restoration of Charles II in 1660 brought with it a strange stability. The king himself, educated in the courts of Europe, had a fascination with mechanics, astronomy, and the arts of measurement. London, his capital, was becoming a crucible of ideas, a city where merchants debated philosophers and artisans discussed geometry over coffee. Here, curiosity was not a crime, it was currency. The camera of the mind pans outward from Gresham College, drifting through the foggy streets to reveal the larger stage of the century. Europe was changing. Commerce, navigation, and exploration were binding the world together in ways unimaginable a generation earlier. The compass, the clock, and the printing press had become the new trinity of human progress. The same rational spirit that drove ships across the Atlantic was now being turned inward, toward the mysteries of air, light, and motion. It was this spirit, restless, practical, and endlessly questioning, that would give birth to what historians later called the scientific revolution. But to those who lived it, it was not a revolution at all. It was a slow illumination, a steady turning of the mind toward evidence. A man could look through a telescope and see the moons of Jupiter. He could weigh air, predict tides, and measure the speed of sound. In doing so, he began to see himself not as a subject of divine command, but as a participant in creation's order. Science, in this age, was not yet an institution. It was an attitude. It meant humility before the unknown, a willingness to test, to fail, and to learn again. The men who met in Gresham College were not seeking power, wealth, or fame. They sought understanding. Their motto, soon to be declared by the Royal Society, captured it perfectly. Nullius in verba, take nobody's word for it. It was a quiet rebellion against authority, and a call to anyone who believed that truth should stand on its own. Beyond the walls of London, empires were expanding. British ships sailed to India, Africa, and the Americas, bringing back not just goods, but knowledge. Plants, minerals, animals, and maps of lands never seen before. Curiosity became a tool of empire, but it was also its conscience. To measure the world was to claim it. To understand it was to question that claim. The pursuit of natural knowledge became inseparable from the shaping of modern power, yet in its purest form, science remained a deeply human act, the attempt to see clearly in a universe vast and intricate. The 17th century, for all its wars and contradictions, carried a quiet heroism. The heroes of this story wielded not swords but instruments, thermometers, lenses, and pendulums. They were driven by wonder more than ambition. And in their experiments, clumsy and profound, they forged a new covenant between humanity and nature. Science, as it emerged from these flickering lights, was not merely a body of knowledge, it was a way of seeing, an agreement that truth should be observable, repeatable, and shared. To weigh air was to humble oneself before it. To map the stars was to admit that they followed laws. To study the heart's motion was to realize that even life itself was governed by patterns that could be known. And yet, even as this new light spread, it did not extinguish the old. Faith did not vanish. It evolved. Many of the first scientists were believers, convinced that by studying creation, they could better understand the Creator. They saw no conflict between reason and reverence, only a bridge. For them, the natural world was not a rival to the divine, but its greatest testament. If you listen closely, you can almost hear their footsteps echoing across the centuries. Boyle and Hooke, Wren and Wilkins, Newton soon to come, men who turned wonder into method and questions into truth. Their experiments would form the foundations of chemistry, physics, and astronomy. But their legacy was larger still. They taught the world that knowledge belongs not to the few, but to all who seek it. The light that flickered in that small London room in 1660 would soon spread across oceans and centuries, illuminating minds and transforming societies. It was a light that asked each generation to look closer, think deeper, and believe that understanding could lead to progress. And even now, in a world far removed from that candlelit night, the same question lingers, quiet but insistent. What do we still have left to discover? If this story stirs something in you, a spark of curiosity, a hunger to understand, then follow it. Subscribe to curiosity itself. Let that same flame guide you, as it once guided them to seek truth not in hearsay, but in discovery, because knowledge, like light, grows brighter only when it is shared. The candlelight trembled again in the long chamber of Gresham College. It was late, too late for most of London, yet the voices inside did not fade. The city outside was silent beneath the fog, but within these walls thought itself seemed to hum. Brass instruments glinted on a nearby table. Glass tubes reflected the light of the fire, and sheets of parchment were scattered like the fragments of an unfinished idea. Around the table sat men whose names would soon become part of a legend, though none of them yet knew it. Robert Boyle, the quiet chemist with eyes both gentle and unyielding, traced a line across his notes. His experiments with air had consumed him for years, and now his mind was filled with questions. What is the true nature of the atmosphere? Can it be weighed, measured, tamed? Beside him sat Robert Hooke, younger, restless, and quick in speech. His fingers, always moving, toyed with a brass lens. the same lens that had once revealed to him the invisible world of the microscopic. Hooke's curiosity seemed boundless, yet it often collided with his temper. To his right was John Wilkins, a churchman with the soul of a philosopher, once chaplain to Oliver Cromwell, now Dean of Ripon, and a man of rare moderation in a polarized age. Near the fire, Christopher Wren, elegant and composed, listened more than he spoke. A mathematician and architect, and soon to be the designer of London's reborn skyline, they gathered not as noblemen but as seekers. Their conversation moved easily between theology and experiment, philosophy and mechanism. On the table lay fragments of strange instruments, an air pump with brass valves, a pendulum clock, sketches of geometric orbits. Outside, the world still belonged to kings and bishops, but here, in this modest hall, a new kind of power was taking shape. The power of understanding. The meeting had no official name. They called themselves, half in jest, the Invisible College. It was not a society yet, only a circle bound by curiosity. Their notes were written in Latin and English, their experiments funded by their own pockets. They met in private because they feared ridicule as much as censorship. For in 1660 the line between discovery and heresy was thin. The air in the room thickened as Hooke demonstrated his latest invention, a more efficient version of Boyle's air pump. He placed a small candle under the glass dome and began to draw the air out. The flame flickered, danced, and finally went out. A silence followed, and then Boyle spoke softly. "So, air sustains flame, and perhaps life itself." Hooke smiled, already thinking of the next experiment. At that moment, the heavy door opened, and a draft of cold air swept through. A young man entered, cloaked and cautious. His hair was dark, his gaze alert but distant. He carried a notebook bound in worn leather. Wilkins rose with a nod. "You must be Mr. Newton, from Cambridge," he said. The newcomer inclined his head slightly. "I have read your discussions of motion, sir," Wren added with quiet curiosity. Newton said little. He was 23 and already possessed that strange stillness of mind that made others uneasy, as though he were listening to something no one else could hear. The conversation resumed. Boyle spoke of the elasticity of air. Hooke countered with the possibility of invisible particles in motion. Wilkins proposed that the same laws might govern the heavens and the earth. Newton listened, taking notes, his pen moving swiftly. The words light, gravity, and motion appeared in the margins of his page. None of them could have known how far those three words would carry human thought. The room glowed with argument and laughter, the clink of glass and the scratch of pens. Ideas collided like sparks, and from their friction came warmth. Hooke sketched a design for a balance that might measure the pull of the earth itself. Wren mused about architecture guided by mathematics, cathedrals that could rise not only toward heaven, but through reason. Boyle wondered whether sound could travel through a vacuum. The questions seemed endless, but none of them sought to end them. The purpose was not certainty, but pursuit. When the hour grew late, the fire burned low. Outside, the first snow began to fall over London, whitening the roofs of a city still recovering from plague and war. Inside, the men lingered, reluctant to part. Boyle closed his notebook and looked around the room. "We are scattered minds," he said quietly, "but perhaps we should not remain so. If truth is to endure, it must have a house." Wilkins nodded. "A fellowship," he said, "of those who love knowledge, not power." Hooke leaned back, smiling. "A brotherhood of experimenters, then." Wren's voice was calm, deliberate. "A society," he said, "dedicated to the improvement of natural knowledge." They fell silent for a moment, as if testing the sound of the idea. Beyond the window, the snow thickened, and the faint toll of St. Paul's bell carried through the night. Boyle rose, gathering his papers. "Let us begin, as we mean to go on," he said softly, "with patience, humility, and proof." He snuffed the candle, and for a heartbeat the room was plunged into darkness. Then another flame was struck, small, persistent, steady. That night, as the wind howled through London's narrow streets, a new chapter of human history began to take shape. It did not begin with a proclamation or a crown, but with a conversation, a handful of men daring to believe that the universe could be read like a book, if only one learned its language. And in that cold, forgotten room at Gresham College, under the watch of a flickering flame, the Royal Society was conceived, not yet named, not yet formed, but already alive, pulsing in the minds of those who believed that knowledge, when shared, could change the world forever. London, 1661. The city was stirring again, its wounds from civil war beginning to close. Bells rang from St. Paul's, not for mourning, but for coronation. England, after years of bloodshed and exile, had a king once more. Charles Stuart, the second of his name, rode through the cheering streets beneath arches of laurel and silk. The Civil War had ended in shadows and silence. A regicide, a republic, and then the weary years of Cromwell's rule. But now the monarchy was restored, and with it returned a strange mixture of nostalgia and curiosity, as if the kingdom itself had been reborn with questions it could not yet answer. Charles II was no ordinary monarch. Years in exile had shaped him into something unlike his ancestors, not a warrior like his father, nor a priest-king like his forebears, but a man of wit, appetite, and restless intellect. In Paris, he had attended salons of philosophers. In The Hague, he had conversed with engineers and navigators. He loved conversation as much as ceremony, and could spend hours discussing geometry, chemistry, or the construction of a clock. His court, when he rebuilt it, was not only a theater of politics, but of experiment, a place where jesters shared the stage with astronomers, and curiosity itself became a royal pursuit. The England he inherited was exhausted, yet fertile. The fires of war had burned away many of its old certainties. The Puritan austerity that had ruled under Cromwell was giving way to a new energy. Laughter in the taverns, trade on the docks, and debate in the coffeehouses. The Navy was expanding, merchants were charting routes to faraway oceans, and London was pulsing with invention. Science, though still whispered of as natural philosophy, was finding its place among the arts of statecraft. The Restoration was not only political, it was intellectual. It was during this restless moment that word reached Whitehall of a group of men meeting at Gresham College. Thinkers, experimenters, and philosophers who sought to understand the world through measurement rather than authority. Their discussions, it was said, touched upon air, motion, light, and the nature of life itself. Charles listened with amusement at first, then with interest. He had always been fascinated by mechanism, clocks, telescopes, and the art of navigation. He saw in their pursuits a reflection of his own desire to understand the workings of both nature and empire. One evening, in his study overlooking the Thames, the king summoned his secretary. "These men of Gresham," he said, "they seek to study nature by experiment, not by opinion. Yes, your majesty, they call it improving natural knowledge." The king smiled. "Then we must give them a place to do it properly." And so, in 1662, the crown issued a charter bearing the royal seal. Its Latin title carefully inscribed, "The Royal Society of London for Improving Natural Knowledge." The parchment, thick and cream-colored, declared the society's purpose to extend the bounds of knowledge of the natural world by experiment and observation. For the first time, a government recognized not just the practice of science, but its moral authority, the right to question. The Royal Charter gave the fledgling society more than legitimacy, it gave it permanence. From now on, its members were not just a club of the curious, but fellows of the Royal Society, men whose discoveries would carry the weight of the crown. Yet Charles II, shrewd and tolerant, did not claim their ideas as his own. He granted them independence, a rare gift in an age when every word and gesture of thought was subject to suspicion. In the candlelit chamber where the charter was presented, Robert Boyle stood beside John Wilkins, Christopher Wren, and Robert Hooke. They bowed as the document was read aloud. When the words, "By the grace of His Majesty for the improvement of natural knowledge," echoed through the hall, they understood that something unprecedented had occurred. The search for truth had been given the blessing of the throne. It was a delicate alliance. Reason and royalty, experiment and empire. Yet for Charles, this marriage of science and state was not merely symbolic. He saw in it the machinery of a new world. If England was to rule the seas, she must master the winds. If she was to expand her dominions, she must map the heavens and understand the tides. Knowledge, he believed, was the surest compass of power. The king himself became, in his way, a patron of the new curiosity. He commissioned experiments on tides at the Thames estuary, ordered designs for better naval instruments, and encouraged the building of observatories. He even attended demonstrations by Hooke, watching with childlike fascination as a pendulum kept time to the beat of his own heart. At court, whispers grew that the king's interests were eccentric, even frivolous. But those who understood him saw something deeper. Charles II had witnessed the fall of his father, the rise of fanaticism, and the fragility of order. He knew that authority built on ignorance could not last. If reason could preserve the kingdom where swords had failed, then he would make reason royal. In the years that followed, the Royal Society became the heart of England's scientific life. It met weekly, its members presenting experiments, debating results, and recording them in meticulous detail. The Society's motto, chosen with care, captured the very spirit of the age, nullius in verba, take nobody's word for it. It was both declaration and defiance, a reminder that truth owed allegiance to no crown but its own. And yet it was Charles's name that adorned the charter, his seal that sanctified their independence. Without him, the flame lit in that modest room at Gresham College might have guttered out. With him, it grew into a beacon that would outshine thrones. Through fog and fire, war and plague, the Royal Society endured, not as the servant of kings, but as the guardian of inquiry. In the decades to come, its fellows would change the world. Hooke with his micrographia, Wren with his domes, Newton with his laws of motion. But on that day in 1662, as the king laid his quill upon the parchment and smiled faintly at the men before him, none of them could have imagined the weight of the gesture. The camera of history lingers on that moment, the ink still wet, the candlelight gleaming on the seal. The king rises, his voice measured and almost playful. "Gentlemen," he says, "see that your experiments are worthy of England." And in that sentence, half command, half blessing, the modern age quietly began. The wax seal on the royal charter had barely cooled when the members of the new society gathered once more at Gresham College. The year was 1662, and London, still soot-stained from war and still whispering of plague, seemed unaware that something quietly revolutionary had taken root within its walls. The king's blessing had given them a name, but names alone did not make a movement. What mattered now was how they would think, how they would work, and above all, how they would prove. On that first evening, after the charter was read aloud, Robert Boyle placed his notebook on the table and spoke a sentence that would come to define their purpose. "Let no man's word stand in place of truth." It was later rendered in Latin, nullius in verba, take nobody's word for it. 3 words, simple yet defiant, that marked the end of one intellectual age and the beginning of another. For centuries, Europe had bowed before authority, of kings, of priests, of Aristotle himself. But here, within the modest halls of Gresham, a new creed was taking shape. That truth must be verified by experiment, not inherited by reputation. The Royal Society's method was not born from theory, but from practice. Their meetings became workshops of the mind, laboratories of conversation, where each claim was tested, recorded, and debated until evidence spoke for itself. On a long oak table lay instruments both crude and wondrous: air pumps, barometers, magnets, prisms, telescopes, and mechanical contraptions that looked like puzzles in brass. Hooke, ever restless, designed most of them with his own hands, hammering precision out of metal and imagination. Every week, they gathered around his devices as he demonstrated the behavior of air, light, or motion, and Boyle, pen in hand, carefully noted every observation. Their approach was disciplined yet open. A typical meeting began with the reading of minutes from the last. Every experiment, every result, every uncertainty. If a candle burned longer in one chamber than another, the fact was logged. If mercury fell or rose in the barometer, it was measured, compared, and debated. Observation first, Wilkins would remind them, then reflection. This meticulous routine, seemingly mundane, was in truth the foundation of modern science: replication, record, and reason replacing tradition, faith, and guesswork. There was something quietly democratic in the air of those meetings. Within those walls, rank mattered less than reason. Boyle, born of aristocracy, worked side by side with Hooke, the son of an island curate. Wilkins, the clergyman-philosopher, conversed easily with craftsmen and sailors who brought instruments from the docks. Christopher Wren, though of gentle birth, listened earnestly to the practical men who shaped glass and brass. In that room, intellect outranked lineage. The society had achieved what few courts or churches could, a fellowship where thought itself was the only nobility. Hooke's restless energy drove much of the society's rhythm. He moved between disciplines as if boundaries did not exist. One day testing the spring of metal, the next sketching the orbit of planets. Boyle admired his ingenuity but worried about his impatience. Wren respected his genius, yet smiled at his eccentricity. Wilkins, ever the peacemaker, often reminded them that diversity of method was their strength. "Let us not argue who is right," he once said, "but discover what is true." Under his guidance, meetings became more structured. A secretary, often Hooke himself, recorded every session. These minutes, later published in Philosophical Transactions, became the first scientific journal in history. They were read not as proclamations of truth, but as invitations to question. Each report began not with conclusion, but with evidence. Each finding, no matter how small, was open to challenge. "Let the world be our witness," Boyle wrote in the margin of his notes, "for truth thrives in daylight." This method, experiment, record, verification, was nothing less than a rebellion against centuries of scholastic tradition. The medieval scholars had argued through syllogisms, weaving reason from words. The men of the Royal Society argued through nature herself. They replaced disputation with demonstration, authority with transparency. In their eyes, a drop of mercury falling in a tube could tell more truth than 1,000 pages of commentary. And yet, despite their seriousness, there was wonder in their work. When Hooke placed a flea beneath his microscope and revealed a miniature world of limbs and armor, the room fell silent in awe. "The hand of the Creator," whispered Wilkins, "visible in what the eye had never seen." When Wren traced the curve of a comet across the night sky, the men leaned forward, realizing they were watching order emerge from what once seemed chaos. And when Boyle's air pump made the bell inside fall silent in vacuum, they understood that even sound obeyed laws. In those moments, science was not cold or mechanical. It was reverent. Their curiosity was a form of worship, their experiments a liturgy of reason. They believed that to study nature was to read the handwriting of God, and that each law discovered was a verse recovered from the lost language of creation. The Royal Society grew quickly, drawing minds from across England and beyond. Mathematicians, astronomers, engineers, physicians, and explorers joined their ranks. Every background, every accent, every discipline found a voice there. To join was to submit to a shared discipline, to test, to doubt, to record. No discovery was final. Every conclusion was provisional. "We are but beginners," Boyle said once, "in the alphabet of nature." As the meetings continued, so too did their rituals. Hooke's drawings filled volumes. Wren's sketches of architectural harmonies inspired designs that would one day rise from London's ashes after the Great Fire. Wilkins dreamed of a universal language of science, while Boyle urged that experiments be shared freely so that truth would belong to no man alone. Their debates were fierce but civil, bound by the understanding that disagreement was not division, but progress. The camera of imagination lingers one evening, candles low, ink drying, the members dispersing into the cold. The secretary closes his ledger, marking another session complete. Outside, the Thames gleams faintly under moonlight. Inside, a single phrase, inscribed on parchment, captures the essence of their age. Nullius in verbis, 3 words that changed how the world would seek truth, a promise that knowledge would no longer bend to power, and that reason, patient and fearless, would light the path ahead. The air in the workshop was dense with the scent of oil and brass. London outside was dim and wet, its alleys glistening with mist, but inside Gresham College, 2 figures labored over a strange machine. Robert Boyle, calm, deliberate, and precise, stood beside the younger and more impatient Robert Hooke. Between them, on a heavy oak table, rested a contraption of glass, copper, and leather tubing. To the untrained eye, it looked like a brewer's folly. To them, it was a portal into nature's secret engine. Hooke bent over the cylinder, adjusting the valves with a small wrench. The candle beside them flickered as he turned the handle, and the sound began. A low, steady hiss, like the breath of an invisible creature. Boyle leaned closer, eyes intent. Within the glass dome, a small flame shivered, then dimmed, then vanished. The room grew silent. Hooke looked up, his face half lit by the remaining candle. "The air is gone," he said softly. Boyle nodded, and with it, life itself. This was their machina boylana, the air pump, the first of its kind to create an artificial vacuum. In a world where philosophers still debated whether nothingness could exist, Boyle and Hooke had built a device that summoned it at will. When they placed a lit candle under the glass and drew out the air, the flame died. When they enclosed a ringing bell, its chime faded into silence as the vacuum deepened. It was as if the very breath of the world had been withdrawn. Hooke, fascinated, began to imagine more experiments: mice, seeds, sound, even weather. Boyle, though equally curious, was more reflective. He saw in each result not merely a trick of physics, but a revelation of order. "In this void," he wrote, "we perceive not emptiness, but the conditions of life itself." They repeated the experiments for weeks, recording every observation with patient care. The hiss of escaping air became the anthem of a new science, a music of precision, of trial and error. Sometimes the glass would shatter under pressure, or the seals would fail, and they would begin again. Hooke's fingers grew calloused. Boyle's notes multiplied. Out of those failures emerged not frustration, but faith. The faith that nature, when questioned properly, would always answer. When The Spring of the Air was published in 1660, it astonished Europe. The title itself was poetic. Spring meant not only elasticity, but also renewal, the living force of air. In it, Boyle described his experiments with clarity and humility, explaining how air behaved like a compressed spring, exerting pressure outward. For the first time, the invisible was being described in measurable terms. The age of speculation was yielding to the age of experiment. In his study, Boyle often paused between experiments, gazing at the modest apparatus before him. To him, the air pump was not merely a machine, it was a mirror of creation, proof that even the most intangible forces could obey laws. "Nature," he wrote, "is not capricious, but consistent. And consistency, once found, could be expressed in numbers." Out of these countless trials came one of the most elegant truths in science, the law that bore his name. Boyle noticed that when the volume of air was reduced, its pressure increased proportionally. The relationship was perfect, precise, and constant. PXV, Schumacher's constant. In those few symbols, the breath of the world became mathematics. He had found a pattern that governed not just air, but the invisible structure of existence. The same law that ruled the pump ruled the lungs, the wind, and even the flight of ships. Mariners began to understand the behavior of wind and pressure. Engineers found ways to harness it in engines and pumps. From weather prediction to diving bells, from steam engines to physics itself, the equation echoed through centuries. And yet, Boyle himself took little pride in authorship. He saw his discoveries not as triumphs, but as testaments, evidence that nature, like Scripture, could be read if one had patience. "I am but a servant of nature," he said, "and she reveals herself only to those who observe in silence." Unlike many of his peers, he refused the vanity of invention. When courtiers praised him as the father of chemistry, he demurred. "I but questioned," he replied, and she answered. He carried this humility into his daily life. Though wealthy by birth, Boyle lived simply, often giving away portions of his inheritance to fund instruments and apprenticeships for others. He believed that knowledge should not belong to one man or one class, but to all who sought it with honesty. His laboratory was open to craftsmen and scholars alike. His experiments were meticulously documented so that any mind, noble or common, could test them. Yet beneath his calm reason lay a conviction deeper still. Boyle was a man of faith, not blind faith, but one refined through reason. He saw no conflict between science and religion. For him, they were two languages describing the same truth. In his journals, he wrote that the study of nature was a form of devotion, an act of gratitude toward its author. To Boyle, every discovery was a kind of prayer, not to replace belief, but to purify it. The order of the cosmos, the harmony of laws, the quiet beauty of a crystal forming or a flame-consuming air, these were signs of a divine intelligence, not of chance. He once said to Wilkins, "When I hold the glass to the light and watch air disappear, I am reminded that even what is unseen has purpose." This belief set him apart in an age of growing skepticism. While others argued that science had dethroned faith, Boyle argued that it had only deepened it. For how, he wrote, could one study the laws of nature without admiration for the lawgiver? His God was not a figure of fear, but of order, a creator who built a world so perfect that its workings could be understood through reason. It was this harmony between curiosity and reverence that defined him. In an era when men still argued whether the heavens moved for divine or mechanical reason, Boyle quietly demonstrated that both could be true. He believed that faith without inquiry was superstition, and inquiry without humility was arrogance. Between those extremes, he found the middle path, the rational devotion of the modern scientist. In 1661, he published The Skeptical Chymist, a book that would redefine chemistry itself. Its title, deceptively simple, concealed a revolution. In it, Boyle rejected the ancient notion of the four elements, earth, air, fire, and water, and proposed that matter was composed of particles in motion, combining and separating according to laws. The tone was not combative but questioning. He wrote not to destroy old beliefs but to refine them. The book's final pages are quiet, almost contemplative. Boyle speaks not as a conqueror of nature but as a witness to its design. "Let us not cease to doubt," he writes, "for doubt is the key that opens knowledge." In that single sentence lies the essence of his life, and of the scientific spirit he helped to shape. In the evenings, after the air pump was covered and the lamps extinguished, Boyle would linger alone in the workshop. The faint hum of London streets drifted through the shutters. On the table before him rested his instruments, the glass dome, the bell, the flickering candle stub. He touched them lightly, almost reverently, as one might handle relics. To others, they were tools. To him, they were scripture, the physical words of a universe waiting to be read. And so he continued, day after day, searching the void not for miracles, but for meaning. In the space where air once was, he had found not emptiness, but truth. A truth that whispered, in its silence, that reason and wonder were never meant to be apart. The light of dawn crept through the narrow windows of Gresham College, cutting faint lines across a table cluttered with lenses, gears, and broken glass. Robert Hooke was already awake, hunched over his instruments, adjusting a screw with a jeweler's precision. His fingers were thin and calloused, his eyes reddened from long hours under the candle. Around him, London slept, merchants, scholars, courtiers, but Hooke was at work, chasing truths too small for the naked eye. He was born far from the world of polished halls and marble staircases, a sickly boy from the Isle of Wight, son of a poor clergyman. His hands, too weak for the plow, were meant for tools. When other children ran in the fields, Hooke took apart clocks and reassembled them to see what made them live. The island air filled his lungs, but his mind already looked to the stars. After his father's death, he traveled to London with a few coins and a head full of ideas. He became an apprentice to a painter, then a student at Oxford, where his restless mind caught the attention of Robert Boyle. It was Boyle who saw in the young man something rare, a combination of dexterity and imagination, of theory and craft. Hooke became his assistant, building instruments for Boyle's air experiments. In time, he would surpass even his master in mechanical genius. He was, above all, a maker. Where others spoke of ideas, Hooke built them. He designed barometers and pendulums, telescopes and microscopes, engines and springs. His notebooks, written in a tight, slanted script, overflowed with sketches and equations. To read them was to walk through a labyrinth of thought. Elasticity, light, motion, fossils, memory, even architecture. The human mind, it seemed, was not enough to contain his curiosity. Yet for all his brilliance, Hooke remained an outsider. In the Royal Society's meetings, he was the one who set up the apparatus, calibrated the instruments, prepared the glass, and measured the results, while others, gentlemen and lords, debated the meaning. Boyle, Wilkins, Wren, and the rest spoke with polish. Hooke worked in silence. He was the craftsman behind the curtain, the man who made knowledge possible but rarely claimed it. "They talk," he once wrote bitterly, "while I do." London's elite saw him as irritable, even difficult. He was impatient with ceremony and had little tolerance for vanity. His genius was practical, his humor dry, his manner sharp. But beneath that edge was a man who never stopped wondering. At night, he would climb the roofs of the college to chart the movement of the moon, or stay bent over a microscope for hours, studying dust, hair, and insect wings. He found poetry in precision. Hooke's most enduring gift to humanity came from those long, sleepless nights. With his microscope, a contraption of brass tubes and polished glass he perfected by hand, he began to peer into a world no one had truly seen before. What he found there would astonish all of Europe. Under the flicker of a single candle, Hooke adjusted the focus. In the circle of light, the leg of a fly appeared enormous, armored like a knight's gauntlet. The wing of a butterfly shimmered with patterns like stained glass. The edge of a razor, seemingly smooth, revealed itself as a jagged mountain range. He looked at cork under magnification and saw it divided into tiny compartments. Cells, he called them, the word still used today. Each discovery filled him with awe. "There is a whole new world beneath our sight," he wrote, "one that has existed as long as the heavens, yet remained invisible." When Micrographia was published in 1665, it was more than a book. It was a revelation. Its copperplate engravings, drawn by Hooke himself, were vast and hauntingly beautiful. Spiders, lice, plants, and minerals filled the pages, rendered with the fidelity of art and the accuracy of science. The book sold out within weeks. Readers who had once stared at the night sky now looked downward, into water droplets, grains of sand, and the fibers of cloth, realizing that the universe was not only above them but also beneath their fingertips. Samuel Pepys, the famous diarist, called Micrographia the most ingenious book I ever read. Philosophers compared it to Galileo's Sidereus Nuncius, which had revealed the moons of Jupiter half a century earlier. But Hooke's world was closer, more intimate, a cosmos hidden in the ordinary. He had shifted the direction of wonder itself. "Hooke opened a new universe," wrote one of his contemporaries, "not in the heavens, but in every drop of water." His images changed how people thought about life. They showed that nature was structured, intricate, and alive at every scale. That divinity could dwell not just in stars, but in the vein of a leaf or the eye of a gnat. But genius in Hooke's time was often a lonely thing. Recognition came unevenly, and admiration was mixed with envy. His work as the curator of experiments at the Royal Society consumed his life. Every week, he was required to present something new. A discovery, a device, a proof. It was a role both glorious and punishing. Few could match his output. Fewer still gave him credit. Then came the growing shadow of another mind, Isaac Newton. At first, they admired each other from a distance. Hooke respected Newton's intellect. Newton acknowledged Hooke's skill. But as their paths crossed more often, in debates on light, color, and the force of gravity, admiration turned to tension. Hooke claimed that light traveled as waves. Newton insisted on particles. Hooke suggested that the planets moved in orbits curved by attraction. Newton would later turn that suggestion into the theory of universal gravitation. Pride clashed with pride. Letters grew cold, then sharp. Hooke accused Newton of borrowing his ideas without acknowledgement. Newton, hypersensitive and defensive, withdrew further into isolation. When Hooke died in 1703, Newton was appointed president of the Royal Society, and under his tenure, Hooke's portrait disappeared from its walls. No likeness of him survives today. It was as if the man who had revealed the invisible world had himself become invisible. Yet history, with time, began to remember. Every microscope, every study of cells, every telescope and mechanical device that measures the world still carries something of Hooke's hand. His law of elasticity, ut tensio, sic vis, as the extension, so the force, remains a cornerstone of physics and engineering. His architectural sketches helped rebuild London after the Great Fire, alongside Wren. His instruments, his methods, his restless curiosity, all these became the quiet scaffolding of modern science. Hooke was never a saint, never a hero of smooth legend. He was impatient, proud, sometimes petty, but profoundly human. His genius was not born of privilege, but of persistence. He built, broke, and built again. He doubted, argued, and returned to his desk until the truth took shape. In the end, his legacy is not measured by fame, but by foundations. The microscope that revealed the cell, the law that defined elasticity, the methods that shaped experimental science, all are stones laid by his hands. If Newton gave the world gravity, Hooke gave it structure. And though no portrait of him remains, his presence endures in every precise measurement, in every lens that magnifies the unseen, in every mind that refuses to stop asking how. The camera of history fades on the image of a man alone in a darkened room, bending over a microscope. The candle burns low, the glass gleams faintly, and in the silence of that moment, between observation and revelation, Robert Hooke still lives, quietly illuminating the small infinities that make up our world. The summer of 1665 came heavy with silence. Across England, bells tolled not for celebration, but for warning. The plague had returned. From London to Cambridge, the streets emptied, the markets closed, and the air itself seemed to hold its breath. At Trinity College, the doors were locked, lectures suspended, and the scholars scattered to the countryside. Among them was a thin, quiet student of mathematics, a man few had noticed, who carried his notebooks home to a small manor in Lincolnshire called Woolsthorpe. His name was Isaac Newton. The house stood alone among fields and apple trees, its stone walls damp from the rain. To most, it was a place of refuge. To Newton, it became a universe in miniature. Here, isolated from the noise of the world, he turned inward, not to escape, but to think. He was 22 years old, and for nearly 2 years he would live almost entirely in solitude, his companions little more than the wind, the pages of Euclid, and the shifting light that crept through the shutters. On one such afternoon, as the plague raged far away and the sun broke through the clouds, Newton sat in the orchard behind his home. He was not idly resting. His mind, like the weather, was in motion, restless, circling questions that had haunted him since Cambridge. Why does the moon not fall? What keeps the planets in their paths? What force binds the earth to the heavens? Then, as he later told the story, a single apple fell from a branch and struck the ground before him. It was a simple thing, an apple falling, as countless apples had fallen before. Yet in that quiet instant, Newton's gaze followed not the fruit, but the invisible line between it and the earth. It is not the apple, he would one day write, but the question that fell. What was this pull that reached through space, drawing the apple downward, the same pull that might perhaps hold the moon in its orbit? Could there be one law, not many, governing both heaven and earth? The thought was radical. For centuries, philosophers had divided the cosmos into two realms: the terrestrial, where things fell and decayed, and the celestial, where perfect spheres moved in eternal harmony. Newton, sitting beneath the tree, dared to believe that both obeyed the same principle. He began to fill his pages with diagrams and numbers, the margins thick with calculations. Every observation led to another question. If the moon's path curved toward the earth as it circled, then the same force that pulled the apple downward might also guide the heavens. The universe, he realized, was not divided. It was bound together by a single, invisible thread. Inside the dim study of Woolsthorpe, experiments became his language of thought. Newton darkened the windows and let in a single beam of sunlight through a hole in the shutter. He held up a glass prism. Sunlight exploded across the wall in bands of color: red, orange, yellow, green, blue, indigo, violet, each distinct, each immutable. Light was not pure, as many believed. It was composed of many lights, each bent by the prism at its own precise angle. He spent days tracing the spectra, measuring the spread, comparing reflections, refractions, and shadows. In his notes, he wrote that light consists of rays differently refrangible. It was a new way of seeing, not through faith or metaphor, but through measurement. The same curiosity that had driven Hooke's microscope now turned toward the heavens, refracted through Newton's lens. At night, he turned to motion. He rolled spheres across wooden floors, swung pendulums, watched falling objects, and timed their descent with makeshift clocks. He was searching for the grammar of the universe, the rules by which motion spoke. The solitude of Woolsthorpe was not emptiness, it was gestation. Each day, Newton peeled back another layer of nature's design. "I keep the subject constantly before me," he wrote, "and wait till the first dawnings open slowly, by little and little, into a full and clear light. Outside, the world suffered, plague in the south, fear in the cities. But in that quiet house, another world was being built. He had no laboratory, no assistance, no funding, only the persistence of a mind unwilling to look away. The very isolation that silenced so many gave Newton the silence he needed to listen to nature itself. By the end of 1666, he had conceived the principles that would define modern science: the laws of motion, the universal law of gravitation, the nature of light, and the foundations of calculus. They were not yet formalized, not yet proved, but they lived already in the margins of his notebooks, equations and sketches that shimmered like constellations across the page. It would be years before the world saw them, and longer still before it understood. But in that plague year, in that quiet orchard and dim study, a revolution had begun. Not of kingdoms or faiths, but of the human mind. Later generations would paint the scene in legend: the apple falling, the sudden flash of understanding. Yet the truth was slower, more patient. The apple was not revelation but confirmation. The final piece in a puzzle he had been assembling all along: the light through the prism, the pendulum swing, the orbit of the moon. All were verses in the same poem, and the poet, solitary and unblinking, was learning to read the language of the cosmos. When winter came, the trees grew bare, the wind colder, and Newton wrote by the dim light of a candle, the scratching of his quill blending with the distant sound of rain. "If I have seen further," he would one day tell a rival, "it is by standing on the shoulders of giants." But in those long, silent months, there were no giants in sight, only a young man alone with the universe, asking questions that had waited since the dawn of time. In the stillness of Woolsthorpe, as disease darkened the land, Newton's world grew brighter, a solitary star burning against the shadow of plague. And in that star's light, the modern age began to see. By the late 1670s, the storm that had once surrounded Isaac Newton's solitude had turned inward. He had returned to Cambridge, where his lectures in mathematics were sparsely attended, his experiments mostly confined to the quiet of his study. The world still knew little of what he had conceived during those plague years in Woolsthorpe. His notebooks, filled with lines of geometry, sketches of orbits, and long Latin phrases, sat unopened on his desk, gathering dust. But one visitor would change that silence. Edmund Halley, a young astronomer of bright intellect and boundless curiosity, came to Cambridge in 1684 with a question. It was a question that had haunted thinkers since Kepler and Galileo. What kind of force keeps the planets moving in their elliptical orbits? Newton listened, then quietly replied, "It is an inverse square law. The force decreases with the square of the distance." Halley stared. "How do you know this?" "I have calculated it," Newton said simply, as if describing the most ordinary of things. That meeting lit a fire that would reshape the world. Halley pressed him to publish, and though Newton resisted, perfectionist, private, wary of criticism, Halley would not let the idea fade. Over the next 3 years, through letters and visits, persuasion and patience, he helped Newton bring together a lifetime of thought into a single monumental work. In 1687, Philosophia Naturalis Principia Mathematica, the mathematical principles of natural philosophy, was printed under the auspices of the Royal Society. Halley, recognizing its importance, personally financed the publication when the Society's treasury could not afford it. Without him, the book that defined the universe might never have seen the light of day. The Principia was not written for casual readers. Its pages were dense with Latin proofs, diagrams, and geometric propositions, but beneath that precision burned a vision as vast as creation itself. Newton had unified the heavens and the earth under one law, one logic, one language, mathematics. He began with 3 simple statements, his laws of motion, that would forever change how humanity understood the physical world. The first law: a body remains at rest or in uniform motion unless acted upon by an external force. It was the quiet revelation that motion does not require cause to continue, only to change. The universe, in Newton's view, was not driven by divine whim, but by inertia, the natural persistence of matter. The second law: the change of motion is proportional to the force applied and occurs in the direction of that force. Here, in a single line, Newton defined cause and effect in the language of numbers. Force equals mass times acceleration. The pulse of every machine, the fall of every stone, the orbit of every planet, each obeyed the same arithmetic. The third law: for every action there is an equal and opposite reaction. It was not merely a principle of mechanics, but a philosophy of balance, a symmetry that echoed through nature and society alike. Push and resistance, impact and recoil, rise and fall, each part of a perfect equilibrium. And then, as if the universe itself had waited for the fourth revelation, Newton turned his gaze upward. From the falling apple to the circling moon, he declared that the same force governs both. This was his law of universal gravitation. Every particle of matter attracts every other with a force proportional to their masses and inversely proportional to the square of their distance. The simplicity was staggering. The force that pulled an apple to the ground was the same that held Jupiter in its orbit and guided the comets through the night. Heaven and earth were not divided. They were one. The cosmos was not chaos, but clockwork. The Principia did not merely describe motion, it described order. In its pages, geometry became prophecy. The orbits of planets, the tides of oceans, even the paths of cannonballs could now be predicted with certainty. What had once been mystery became mathematics. At the Royal Society, Boyle's generation of experimenters read it with astonishment. "Here," one of them said, "is the architecture of the world itself." The Society's motto, nullius in verba, take nobody's word for it, had found its ultimate expression. Newton had not asked the heavens for revelation, he had measured them. Halley oversaw the printing himself, checking each proof, correcting errors, and ensuring the figures were exact. The cost nearly ruined him, but he never regretted it. When the first copies arrived, bound in leather and sealed with the Royal Society's crest, Halley wrote to Newton, "I rejoice exceedingly that so noble a truth hath at last been made known." In the Principia, the union of mathematics and physics achieved something no philosopher had ever dared. It made the universe legible. To think in numbers was to speak, for the first time, in the language of creation. From that moment, science became not just a method, but a vocabulary, a way of reading the divine handwriting in the fabric of space and time. If Galileo opened humanity's eyes, the narrator might say, then Newton taught it how to see the structure of the heavens. The book spread through Europe like dawn. Scholars from Paris to Berlin, from Florence to St. Petersburg, read it in wonder. Some wept at its beauty. Others feared its precision. Leibniz called it the poetry of reason. Voltaire would later write, "After Newton, men will be able to explain the world without appealing to miracles." But Newton himself remained distant from the noise his work created. He disliked fame and preferred the company of solitude. "I do not know what I may appear to the world," he once said, "but to myself I seem to have been only like a boy playing on the seashore, finding a smoother pebble or a prettier shell, while the great ocean of truth lay undiscovered before me." And so, in the twilight of that age, as candlelight flickered over the pages of the Principia, the universe changed forever. The heavens no longer needed the music of angels to move, they moved by law. The same logic that governed the apple governed the stars. The mind of one man had traced the arc of creation from orchard to infinity. The voice of reason had found its rhythm, and the cosmos, at last, could be read. By the dawn of the 18th century, the man who had once sat alone beneath an apple tree was now the most powerful intellect in Europe. Isaac Newton, no longer the reclusive scholar of Woolsthorpe, had become the very embodiment of reason's authority, a figure whose mind seemed to stretch from the Royal Society's chambers to the vault of heaven itself. In 1703, Newton was elected president of the Royal Society, a post he would hold for nearly a quarter of a century. The society that had once been a gathering of curious men in candlelit rooms was now a formal institution, and under Newton, it became something greater still, the temple of modern science. Each Thursday evening, the great hall of Gresham College glowed with conversation and the faint scent of ink and wax. Experiments were prepared on long oak tables, and secretaries waited with quills poised to record every observation. Newton presided at the head, stern and deliberate, his powdered wig immaculate, his gaze sharp. He demanded precision, patience, and proof. No speculation without evidence, no theory without mathematics. The Royal Society's motto, nullius in verba, take nobody's word for it, found its true enforcer. Under Newton, that phrase became a creed. Every claim required demonstration, every experiment demanded replication. He standardized minutes, procedures, and methods of communication. The Society's Philosophical Transactions, the world's first scientific journal, became the blueprint for modern research. Written records, peer review, the slow but steady march from question to certainty. Science, once a gentleman's hobby, became a discipline of rigor and accountability. In Newton's world, truth was not proclaimed, it was proven. Yet even in his ascendancy, Newton remained a man of paradoxes. He was methodical and majestic, but deeply private, rational to the world, yet mystic in his own heart. Beneath the precision of mathematics lay a mind still haunted by the divine. A man who studied alchemy by candlelight and searched for hidden patterns in Scripture, even as he defined the laws of the cosmos. In those years, Newton's intellectual empire grew, but so too did his solitude. Friends became disciples, rivals became enemies, and every conversation seemed to orbit his intellect. Among those orbits were two that would define his later life: Edmund Halley, his loyal supporter, and Gottfried Wilhelm Leibniz, his rival across the channel. The evening was imagined often, but it might well have taken place in spirit. A candlelit room, three great minds, and a single question: what is truth in the language of numbers? Halley, ever the mediator, raised a glass. Gentlemen, the stars obey your equations. Must we quarrel over who first wrote the grammar? Leibniz smiled thinly. It is not the writing I contest, but the spirit. My calculus is a language, fluid, symbolic, clear. His, he nodded toward Newton, is mechanical, bound in geometry like an old cathedral. Newton's eyes flickered with controlled disdain. Language without foundation is poetry, not science. Symbols may be elegant, but truth is not in their beauty. It is in their necessity. Halley interjected gently. And yet, without Leibniz's notation, few would read your Principia without despair. The silence that followed was thick with brilliance and pride. In that imagined dialogue lay the tension of the age itself, the rivalry between intuition and rigor, between continental philosophy and English. Empiricism. Both men sought truth, but through different paths. The dispute over calculus, who discovered it first, who expressed it best, would span decades, letters, and reputations. In truth, both had glimpsed the same horizon from different sides of the sea. But history under Newton's presidency and England's rising power favored the man who ruled from London. Still, Newton was not content merely to reign over science. His influence extended into the machinery of empire. As master of the royal mint, he reformed the nation's currency, introduced measures against counterfeiting, and stabilized the British pound. It was as if the man who had weighed the planets now weighed gold with equal precision. Reason had entered the mint, the courtroom, and the marketplace. But within that triumph, there was loneliness. Visitors described Newton's house as orderly but cold, filled with instruments, charts, and silence. He dined alone, wrote late into the night, and guarded his privacy fiercely. He who thinks half as much as Newton, a French visitor once said, must sleep twice as long. And yet, in his solitude, Newton shaped the culture of knowledge itself. The Royal Society under his leadership became a new kind of court, one where arguments were not won by rhetoric, but by reason. Its currency was data. Its power was proof. Across Europe, kings, merchants, and explorers sought its approval. The experiments in its halls echoed in every academy to come. In Newton's lifetime, the boundaries of understanding expanded more than in any century before. The telescope reached deeper into space, the microscope further into life. Ships navigated by calculation, architects built with symmetry, and philosophers dreamed of universal laws. The world had learned to think mathematically, mechanically, methodically. He had not merely studied gravity, he had institutionalized certainty. As the years waned, Newton rarely appeared in public. He walked slowly, stooped, yet his mind remained as crystalline as the prisms he once held to the light. When he spoke, his words carried the quiet authority of a man who had measured both motion and mankind. He died in 1727, buried with the honors of a king in Westminster Abbey. Above his tomb, carved in Latin, were the words, "Let mortals rejoice that such and so great an ornament of the human race existed." The camera of history might linger on that moment, a procession of scholars, the echo of footsteps on marble, a candle burning low beside his monument. The voice of narration, calm and reverent, might whisper, "A solitary man turned intellect into empire." The empire was not of land or crown, but of truth, a dominion built not by conquest, but by understanding. And through that empire, the human mind, once bound by superstition and fear, learned to walk freely among the stars. The death of Isaac Newton in 1727 did not dim the light he had kindled. It only changed its form. The age that followed, the 18th century, became known not for one man's genius, but for the shared brilliance of thousands. Across Europe, from London to Paris, from Amsterdam to Florence, the air seemed charged with a new electricity, the belief that knowledge could move as freely as the wind. What Newton had proved with his equations, the world now sought to enact with its institutions. The Royal Society, once a modest fellowship of experimenters, became the beating heart of a vast and growing network, a web of letters, journals, and societies that stitched together the minds of an entire continent. Each week, ships leaving the port of London carried not only sugar and silk, but also sealed packets of correspondence. Inside were manuscripts written in Latin and French, pages of diagrams and tables, and reports of strange phenomena. A comet observed in Tuscany, a new lens perfected in Leiden, a botanical discovery from the Caribbean. The Republic of Letters, as it came to be called, had no borders. Its citizens were philosophers, artisans, and astronomers. Its currency was curiosity. The Royal Society's Philosophical Transactions, the world's first scientific journal, became its messenger. Founded in 1665, but truly flourishing in the early 18th century, it carried the voice of reason farther than any ship or sermon. Printed in elegant type and distributed to scholars from Edinburgh to Rome, it was the first publication to make science a conversation rather than a secret. Each issue was a tapestry of wonder. One page might describe experiments on air pressure, another an account of a volcanic eruption near Naples, another the anatomy of an exotic bird brought from the East Indies. Letters were addressed formally to the Right Honourable the Royal Society of London for improving natural knowledge. Yet within them, the tone was one of shared discovery. A French chemist could challenge an English engineer. A Dutch optician could refine the measurements of a Venetian astronomer. And always the reports returned to London, where clerks copied and compiled them, and Newton's successors debated their meaning under the glow of oil lamps. It was a revolution of communication as much as of science. The printing press, once used to spread theology and politics, now printed the very mechanics of the universe. Diagrams of prisms and planets replaced portraits of kings. In the reading rooms of Paris, the drawing offices of Amsterdam, the salons of Vienna, people began to speak in a new tone, precise, empirical, universal. If the 1600s had belonged to the pioneers, the 1700s belonged to the networkers of knowledge. Royal academies rose like constellations across Europe. The Académie des Sciences in Paris, the Accademia del Cimento in Florence, the Leiden Society of Sciences, and dozens of local clubs that met in coffeehouses, printing shops, and private homes. Their members wore powdered wigs and lace cuffs, but in their hearts they were mechanics of meaning, testing, writing, and debating as though the world itself were a laboratory. No longer was science confined to cloisters or castles. It lived in correspondence. in the quiet rustle of paper, in the scratch of quills across borders. One experiment in London might inspire another in Lyon, then another in Lisbon, and within months, its results would be read aloud in St. Petersburg. Knowledge now traveled faster than armies. The process mirrored the expansion of commerce. As merchant fleets crossed the seas with spices, silver, and textiles, so too did they carry the traffic of ideas. Navigation charts improved with Newtonian physics. Shipbuilders consulted mathematicians. Naturalists aboard trading vessels collected samples for the scholars waiting back home. Science had become part of the very machinery of empire, a companion to exploration, an invisible compass guiding progress. Letters from missionaries in China described magnetic compasses and porcelain glazes. Travelers from the South Seas sent back sketches of coral reefs and marine life. Astronomers at colonial observatories compared their readings with those in Greenwich, synchronizing time itself across continents. For the first time, the world began to think as one, not in language, but in measurement. The age's confidence was boundless. A London merchant could read a French paper on the laws of motion while waiting for cargo from India. A Parisian philosopher might quote a Dutch botanist in his essay on morality. Scholars corresponded like traders, bartering discoveries, exchanging methods, and crediting one another in the shared pursuit of understanding. Coffee houses became their ports, loud, smoky spaces where pamphlets passed from hand to hand, and arguments lasted longer than the cups they were served in. Here, merchants and mathematicians sat side by side, debating the tides, the markets, and the stars. What is truth, one might ask? That which can be demonstrated, came the reply. It was a small miracle of civilization, the idea that knowledge could be public, not private, collective, not divine. In Paris, Voltaire wrote that the English have taught us how to reason. In London, Joseph Addison wrote that letters are the engines of light. In Amsterdam, presses thundered day and night, sending out works in multiple languages, from anatomy to astronomy, each claiming its place in the widening orbit of enlightenment. Through these networks, the dream of the Royal Society spread like dawn. It no longer mattered whether a scientist prayed in Latin, French, or Dutch. The language of evidence was the same everywhere. And in that shared grammar of numbers and observation, Europe discovered its first true unity. The camera of history might pan slowly over maps and manuscripts, over candlelit rooms where men and women leaned close to decipher equations, over ports where ships unloaded crates of fossils, plants, and minerals. The narrator's voice might murmur, "From London's gray skies to the blue domes of Florence, the same fire was spreading, not of conquest, but of comprehension." The Enlightenment had begun to breathe, and through its invisible veins of ink, paper, and exchange, the spirit of Newton's reason coursed through a continent, turning curiosity into connection, and connection into civilization. By the middle of the 18th century, the quiet world of observation and theory had begun to roar with the sound of machines. The spirit of experiment, once confined to laboratories and lecture halls, had spilled into the workshops, shipyards, and foundries of Europe. What had begun with glass lenses and air pumps now found form in iron, steam, and fire. The line between philosopher and engineer blurred. The same hands that once adjusted telescopes were now fitting pistons. The same minds that had mapped the stars were now redesigning the engines that powered ships and mills. Science was no longer an abstract pursuit of truth. It had become a tool of transformation. In smoky workshops along the Thames and the Clyde, inventors and craftsmen read Newton's Principia not as scripture, but as blueprint. The principle of force and motion, the laws of pressure and heat, the predictability of cause and effect, all became the raw materials of invention. From this marriage of reason and metal, the steam engine was born. At first, it was crude, a furnace, a piston, and a beam that groaned like a living thing. But under the minds of men like Thomas Newcomen and James Watt, it evolved into a heartbeat of power. Water was lifted from mines, wheels turned, ships sailed upriver against the current. Steam, once a curiosity of physics, became the breath of industry. Every improvement carried the echo of experiment. The careful measurements of Boyle's air pump, the studies of heat by Hooke and Papin, the mathematics of motion from Newton, all converged in the rhythmic hiss of the engine. It was as if the laboratories of the 17th century had begun to move, to breathe, to build. The telescope extended man's sight to the stars. The microscope revealed the hidden worlds beneath his feet. Between them lay the compass, small, humble, yet world-changing. Mariners once steered by faith and instinct. Now they navigated by magnetism and mathematics. The same experimental precision that ruled the heavens now ruled the seas. With better instruments came longer journeys, and with longer journeys came empire. Scientific progress was no longer a private curiosity. It became the infrastructure of power. Observatories tracked the movement of planets to calculate longitude for ships. The British Navy, guided by new maps and better clocks, crossed oceans with unprecedented accuracy. The chronometer of John Harrison, a miracle of mechanical precision, allowed sailors to tell time at sea, and, in doing so, to know exactly where they were on Earth. From the decks of exploration vessels, science and empire marched together. Botanists cataloged plants for medicine and trade. Surveyors mapped coastlines for conquest. Engineers built harbors, canals, and machines that turned distant colonies into extensions of European ambition. Knowledge was no longer just enlightenment. It was strategy. The same empiricism that had liberated the mind now disciplined the world. In hospitals, physicians began to test treatments rather than trust tradition. In universities, chemistry replaced alchemy. Anatomy replaced superstition. The scalpel and the lens became symbols of the same creed: observe, measure, verify. Even the language of power began to change. Kings no longer ruled only by divine right. They ruled by data. Reports, statistics, and surveys became instruments of governance. To know, Francis Bacon had written a century earlier, is to command. Now his words had become the unspoken law of an age. The world's great powers, Britain, France, the Netherlands, built laboratories alongside arsenals, observatories beside fortresses. Knowledge became a weapon sharper than any blade. It charted the winds, cured disease, and conquered distance. And yet, for all its grandeur, this new world still owed its pulse to a single truth: that every revolution of metal, every voyage across the sea, every discovery under glass began the same way, with a question. The question that had once stirred in a candlelit chamber at Gresham College: what is the nature of the world, and how may we know it? Now powered ships, lit factories, and carried nations across oceans. Science had stepped out of the study and into the street. The hum of engines replaced the scratch of quills. And from the laboratories of the mind rose the workshops of the modern world, where curiosity became commerce, knowledge became empire, and experiment became destiny. By the late 18th century, the rhythm of discovery had become the rhythm of civilization itself. The engines of knowledge, once confined to the halls of London, now pulsed through Paris, Philadelphia, and beyond. The Royal Society's creed, that truth must be tested, not declared, had become the faith of an age. From London, that light traveled outward, refracted through languages and nations. In Paris, it found a voice in Voltaire, who returned from England dazzled by the sight of reason made real. He had visited the laboratories, attended meetings of the Royal Society, and spoken with men who measured the heavens rather than speculated about them. In London, he wrote, one finds philosophers who are citizens, and citizens who are philosophers. He carried that revelation back to France like a lantern, lighting the salons of the Enlightenment. In those salons, the air shimmered with argument. Diderot, the restless mind behind the Encyclopédie, took the Royal Society's method, the careful observation, the demand for proof, and transformed it into a cultural revolution. Each entry in his vast encyclopedia was an act of rebellion against ignorance, a declaration that human knowledge could be cataloged, improved, and shared. We will gather all the knowledge of the world, he wrote, so that future generations will not need to ask what we once asked in the dark. Across the ocean, the same flame burned in a different language. Benjamin Franklin, printer, inventor, and statesman, read the Philosophical Transactions in Philadelphia and saw in it not just science, but democracy. When he flew his kite into the storm to capture lightning, he was not only proving that electricity and thunder were one, he was proving that nature obeyed reason, not rank. Franklin corresponded with members of the Royal Society, who later elected him a Fellow, a recognition that symbolized how the Republic of Science had become global. In taverns and academies, in Parisian cafes and American workshops, people began to speak as equals in the language of experiment. Knowledge no longer flowed downward from monarchs or priests. It circulated horizontally between thinkers, craftsmen, and dreamers. The experimenter's lens, once aimed at nature, now turned subtly toward society itself. If laws could govern the motion of planets, could they not also govern the affairs of men? This was the essence of the Enlightenment spirit, that the world, in all its chaos and complexity, was intelligible, that ignorance was not a curse but a problem to be solved, that truth was not owned but discovered. The candle lit in Newton's England now flickered across continents, its light reflected in the ink of encyclopedias, the sparks of electrical experiments, the words of constitutions. From London, the narrator might say, the light traveled outward, across the Channel, across the Atlantic, across the mind of humankind, and though the cities differed, the fire was the same. The quiet, relentless belief that reason could remake the world. It was a cold night in March 1781, the kind of night when England seemed to hold its breath. Over the quiet town of Windsor, the sky stretched wide and still, a black sea studded with points of silver. In a small garden behind a modest brick house, a man stood alone beside a telescope, not a gentleman of science, not a nobleman, but a musician turned astronomer, his hands calloused from both strings and stars. His name was William Herschel. The telescope was his own creation, a massive cylinder of metal and glass, taller than the man himself, assembled from scraps and sleepless nights. By day, he gave music lessons to survive. By night, he built instruments to chase the heavens. He polished mirrors by hand, ground lenses with his sister Caroline by candlelight, and recorded every faint shimmer above the horizon. What began as curiosity had become devotion. On that particular evening, as frost crept along the edges of the lens, Herschel tilted the telescope toward the constellation Gemini. He was cataloging double stars, methodically marking their positions, but something caught his eye. A disk, pale and steady, larger than a star, smaller than the moon. It did not twinkle, it moved. He adjusted the focus, his heart pounding. It was no comet, its orbit was too regular. He observed it night after night, measuring, calculating, comparing. The more he studied, the more impossible it became to deny. He had found a new planet, one beyond Saturn, something unseen by any human eye since the dawn of history. The discovery stunned Europe. The Royal Society, upon receiving his letter, verified the observations and announced the finding to the world. They named it Uranus, the first planet discovered in modern times, and the first to be found with a telescope, not the naked eye. For centuries, humanity had believed that the solar system was complete, the heavens fixed. But now, with one amateur's lens and a little patience, that certainty shattered. The cosmos had grown larger overnight. In that moment, William Herschel became a symbol of something far greater than astronomy. He embodied the democracy of discovery, the belief that truth belonged not to class or rank, but to anyone willing to look carefully enough. The Royal Society, true to its creed, welcomed him as a fellow. A self-taught man from Hanover, once a street musician, was now counted among the greatest minds of England. The image was cinematic. Herschel, in the dark garden of Windsor, wrapped in a coat against the chill, his breath misting in the air. The giant telescope loomed like a cathedral spire, pointing toward infinity. Above him, the stars turned silently in their courses, unaware that one of their own had just been found. His sister Caroline Herschel, too, became part of the story, recording his notes, cleaning mirrors, later discovering comets of her own. Together, they turned a backyard into an observatory, a home into a portal to the universe. Herschel's discovery marked more than a scientific milestone. It was a moral victory for the spirit of inquiry. It reminded a century intoxicated by progress that knowledge was not owned, it was earned, one observation at a time. In the candlelit halls of the Royal Society, where gentlemen in powdered wigs once debated the weight of air, they now spoke with reverence of a man who had lifted his eyes higher. The narrator might say, "From the quiet of Windsor, a musician raised a mirror to the sky, and found reflected in it not just a new planet, but the boundless reach of human curiosity. For if Newton had taught mankind the structure of the heavens, Herschel showed that the heavens themselves were still unfolding. By the middle of the 19th century, the telescopes of the Royal Society had turned inward. The stars had been measured, the planets charted, but the next frontier was life itself. The question that haunted London's thinkers was no longer what lies beyond the sky, but what lies beneath our own skin. And into this world of steam, empire, and inquiry stepped Charles Darwin, quiet, methodical, and endlessly patient. Born into comfort but drawn to nature, Darwin was not a man of laboratories or telescopes. His observatory was the deck of a ship, the HMS Beagle, which in 1831 carried him across oceans to the edge of the known world. For 5 years, he collected, observed, and wondered. On the cliffs of South America, he studied fossils embedded in stone, ancient creatures half known, half forgotten. On the Galapagos Islands, he watched finches and tortoises, each adapted in subtle ways to their tiny worlds. He took notes obsessively, as if the earth itself were dictating its secrets through the rhythm of the waves. When he returned to England, he did not rush to proclaim his findings. For 2 decades, he worked in silence, sorting, comparing, questioning. He was a fellow of the Royal Society, yet he knew that the truth he carried might unsettle the very foundations of belief. In 1859, his book On the Origin of Species finally appeared, a work as seismic as Newton's Principia, but aimed not at the heavens, rather at life itself. Its argument was as simple as it was radical, that all living things, from the smallest insect to humankind, were bound together by a single law. Natural selection, the slow, relentless process by which nature shapes its own creation. Just as Newton spoke of the stars, one commentator wrote, "Darwin has spoken of us." The impact was immediate and electric. Churches and universities alike filled with debate. Preachers saw in Darwin's words a challenge to divine order. Scientists saw a new architecture of life. To some, he had dethroned humanity. To others, he had ennobled it, showing that to understand ourselves, we must first understand the forces that made us. The clash between faith and reason became one of the defining dramas of the 19th century. In crowded lecture halls, men in black coats and white collars argued not about scripture, but about fossils. The famous debate at Oxford in 1860, where Bishop Wilberforce and biologist Thomas Huxley crossed words, captured the moment perfectly: a world standing at the edge of an old age and a new one. Huxley, later known as Darwin's Bulldog, defended the theory not as rebellion, but as revelation, another step in humanity's long journey from ignorance to understanding. "It is better," he said, "to be the offspring of an ape than the child of false pride." Through it all, Darwin himself remained calm, even hesitant. He avoided confrontation, preferring letters and evidence to argument. His writing was gentle but relentless, his tone humble yet certain. Like Newton before him, he had no wish to overthrow faith, only to expand truth. Within the Royal Society, his work was treated not as heresy, but as heritage, the next chapter in the same story of curiosity disciplined by observation. His diagrams of branching species were not so different from Herschel's star maps or Hooke's sketches of cells. They all pointed toward the same conviction, that nature, vast and varied, could be known through patient study. Outside, the world transformed. Factories thundered, railways split the countryside, and microscopes revealed worlds within worlds. Science no longer merely described the universe, it was beginning to reshape it. Darwin's theory gave humanity a new narrative, not a tale of divine design, but of endless transformation, fragile, slow, and astonishing. It placed humankind back within nature's embrace, not above it. And in that shift lay both humility and wonder. The narrator might say, "From the stars of Newton to the shells of Darwin, the same question endures. What is our place in the grand order of things? The answer, still unfolding, lies not in the heavens above, but in the life that surrounds us and within us." If the Royal Society had once opened the heavens, Darwin opened the mirror, and humankind, for the first time, began to truly see itself. By the final decades of the 19th century, the Royal Society had become more than a fellowship of scholars. It was the silent architect of the modern world. The age of observation and experiment had matured into an age of invention and transformation. The same curiosity that once pointed a telescope to the heavens now shaped engines, wires, and circuits. From steam to electricity, from chemistry to computation, the Royal Society stood at the heart of a world being remade by human hands. The Industrial Revolution had already changed how people worked and lived, but now came the second wave, the scientific revolution within industry itself. The scene could be imagined as cinematic. London, 1880s. Factories glowed at dusk. The air shimmered with heat and ambition. Inside, machines pulsed like metal hearts, powered by laws first tested in quiet laboratories. Far from the solemn halls of Gresham College, science had escaped into the streets. It powered locomotives, illuminated cities, and hummed through the new telegraph lines that stitched continents together. In the meeting rooms of the Royal Society, discussions turned from the stars to the forces of the invisible. Magnetism, radiation, electricity. Experiments once done for curiosity were now performed with purpose: to build, to connect, to harness. The discoveries of Faraday and Maxwell, the invisible dance of electric and magnetic fields, gave rise to engines, generators, and the first communications technology of a global age. Chemistry, too, found new meaning. The Royal Society encouraged studies that refined steel, dyes, and medicine, transforming craft into science, and science into industry. The alchemy of the past had finally fulfilled its promise, not to make gold, but to make progress. The Society's fellows became the builders of modern civilization. James Clerk Maxwell's equations mapped the unseen forces that would one day power radios and computers. Lord Kelvin measured temperature and energy with precision that defined the age. Humphrey Davy's experiments on gases and elements led to discoveries that lit lamps and cured diseases. And, through it all, the Royal Society remained true to its founding creed, nullius in verba. Take nobody's word for it. Every engine, every experiment, every equation was born of that same stubborn demand for proof. By the dawn of the 20th century, steam had given way to current, coal to electrons. The world was no longer merely mechanical. It was electrical, chemical, and alive with possibility. The narrator might say, from the flicker of a candle in Gresham College to the glow of electric light across the Thames, the Royal Society's flame endured, changing shape, but never fading. It had guided mankind from the whisper of steam to the hum of the machine, and onward toward the age of invention that would define the modern world. At the dawn of the 20th century, the quiet flame that once flickered in a London college had grown into the blinding glow of laboratories around the world. The age of reason had matured into the age of discovery, and the Royal Society, born in candlelight and curiosity, now stood at the center of a century that would redefine what it meant to know. The world was no longer content to observe the heavens or map the earth. It was beginning to look inward into the invisible fabric of nature itself. From the atom to the gene, from the depths of time to the birth of the universe. The quest to understand creation had become a shared human endeavor, carried forward by minds that were both bold and disciplined. Among them was Ernest Rutherford, a man whose New Zealand accent and booming laugh filled lecture halls with life. He had the manner of a teacher and the vision of a pioneer. Through his experiments, he split the atom and revealed the secret structure of matter, transforming an idea into a force that would power the modern world. His students would go on to shape the 20th century, some building the future of energy, others warning of its dangers. When he spoke of discovery, it was with a sense of wonder rather than conquest. He believed, as the founders of the Royal Society had, that knowledge was not a possession, but a responsibility. In the decades that followed, science turned its gaze from the structure of matter to the mystery of life. In a small room filled with paper models and coffee cups, Francis Crick and James Watson pieced together a shape that would change everything: the double helix of DNA. They were young, reckless, and hungry for truth, and in 1953 they announced that the code of life was written not in divine script, but in the language of molecules. Theirs was not an act of rebellion, but of revelation, a continuation of the same question that had begun centuries before. What are we, and how did we come to be? In another corner of England, long after the atom had been split and the gene decoded, a man named Stephen Hawking sat before a computer, his body frail but his mind soaring. Through mathematical symbols, he reached beyond galaxies, tracing the origins of time and the destiny of space. His theories about black holes and the universe's beginning were not just physics, they were poetry in the language of numbers. Bound to a wheelchair and speaking through a machine, he embodied a paradox. A man trapped in matter, yet free in thought. Like Newton before him, he showed that even the limits of the body could not restrain the power of the human mind. Through each generation, the Royal Society remained a quiet witness to transformation. It no longer belonged only to England, but to the world. Its halls, once filled with gentlemen in powdered wigs, now echoed with voices from every continent. Scientists from India, Africa, the Americas, and Asia joined the fellowship, each carrying new questions and new visions. The Society's journal, once a collection of handwritten letters, now published discoveries that would alter medicine, communication, and technology. From antibiotics to computers, from radar to satellites, each advancement carried within it the same enduring belief. Truth is not found by authority, but by evidence. Outside the laboratories, the world was often turbulent. Wars divided nations, ideologies clashed, and science itself was tested by the power it unleashed. The atom that Rutherford had opened became both a beacon and a warning. The Royal Society, standing between invention and conscience, urged that knowledge must serve life rather than destroy it. For centuries, it had been a house of questions, and now it became a guardian of responsibility. Its members debated not only how to discover, but how to preserve, how to use the gift of understanding without extinguishing what it sought to protect. As the 20th century advanced, the instruments of science grew ever more intricate. The telescope reached beyond the Milky Way. The microscope revealed the structure of viruses, and the computer began to think alongside its creator. The boundary between imagination and technology blurred. Scientists no longer asked whether the universe could be known. They asked how much of it remained hidden. And still, beneath the hum of machines and the glow of screens, one ancient rhythm endured. Observe, measure, verify. In a world of noise and speed, the Royal Society stood as a reminder of patience. Progress was not born from miracles, but from method. Behind every discovery lay decades of failure, correction, and collaboration. The Society's creed, nullius in verba, take nobody's word for it, echoed across laboratories, universities, and data centers. It was a call to humility in an age of certainty, a reminder that truth is not a possession, but a pursuit. By the end of the century, the Society had become a bridge between eras, the living thread connecting Newton's candlelight to the neon of the modern world. It was no longer just a building in London, it was an idea that had survived kings, revolutions, and wars. It had carried humanity from alchemy to atoms, from observation to innovation. The questions had changed, the tools had evolved, but the spirit was the same, the relentless belief that nature, however vast or complex, could be understood. The city around it had transformed beyond recognition. Glass towers rose where gas lamps once burned, and data flowed invisibly through the air where once only smoke had drifted. Yet inside those towers, under the same sky that Boyle and Newton had studied, the descendants of that first generation still worked, testing, measuring, questioning. They no longer wondered whether the world could be known. They asked instead how to know it wisely. The journey that began in the flicker of a candle now glowed across the surface of a planet lit by science itself. The heirs of that small fellowship at Gresham College still pursued the same quiet dream. To understand the world not through fear, but through reason, not to rule it, but to learn its language. And through them, the light that had guided centuries still burned, steady, patient, and alive in a world that more than ever needed its warmth. The 21st century opened not with the triumph of certainty, but with the return of questions. The instruments of science had grown sharper than ever, telescopes that could see the edge of creation, microscopes that could map the code of life itself. But the human world beneath them had become tangled in doubt, fear, and noise. The same intellect that had once lifted civilization now faced its reflection, a planet transformed by its own discoveries. Inside a glass-walled meeting room overlooking London, the emblem of the Royal Society glowed faintly on the polished table. Around it sat not the powdered wigs of Boyle and Newton, but a new generation, men and women of every color and language, their laptops open, their voices calm but urgent. Outside, data pulsed through invisible networks. Inside, they spoke of power, of responsibility, of the line between progress and peril. The questions had changed since Gresham College, yet the weight of them felt the same. What should we do with the power to split the atom, to rewrite the gene, to shape the climate of a planet? Could human reason, the same force that unlocked nature's laws, now guide the moral compass of its own creation? Nuclear energy, once hailed as the promise of infinite progress, had revealed its double face, clean power, and catastrophic potential. The scientists of the Royal Society, heirs to a tradition of measured truth, found themselves mediators between invention and restraint. They spoke in conferences, advised parliaments, and reminded nations that every discovery carried an echo of responsibility. We have learned, one of them said, that mastery of nature is not freedom from consequence. Then came the questions of the environment, vast and immediate. The hum of machines had filled the world, but so too had the smoke of their exhaust. Ice melted, oceans rose, forests fell. The Royal Society turned its gaze from stars and atoms to the fragile balance of Earth itself. Through climate reports and public statements, it called for what few dared to demand: truth before convenience, science before politics. In an age of slogans and denial, its calm voice carried the weight of centuries. Biotechnology brought new miracles and new fears. Genes could now be edited as easily as text on a screen. Diseases once incurable could be cured. Life itself could be redesigned. The promise was breathtaking, but so was the peril. The Royal Society gathered ethicists, engineers, and biologists in the same room, urging that knowledge must never outpace wisdom. It was no longer enough to ask, can we? The greater question was, should we? Outside its walls, a new storm raged, not of war, but of information. In the vast networks of the digital world, truth became slippery, blurred by speed and sensation. Misinformation spread faster than evidence, outrage louder than reason. Once again, the Royal Society became a guardian of clarity, defending the integrity of data, the value of evidence, and the patient art of doubt. The hardest truth to keep, one fellow said quietly, is the one that demands we think before we believe. In this new century, science itself had to learn humility, to remember that every equation began with a question mark. The Society's reports no longer simply announced discoveries. They sought dialogue. They worked with governments not to dictate, but to guide, offering knowledge as compass, not command. Whether in debates on artificial intelligence, pandemics, or climate intervention, the Society's voice was steady, free from the fever of ideology. It had survived kings and revolutions, and it would survive noise. The meeting room brightened as the afternoon sun slid through the glass. Reflections shimmered across the table where old and young debated the same eternal tension: curiosity versus caution, discovery versus doubt. On the far wall, the faint words still glowed: the Royal Society of London for Improving Natural Knowledge. A silence fell for a moment as one of the younger members looked around the room. "Do you ever wonder," she asked softly, "what they would think of us, the founders?" An older scientist smiled. "They would recognize us," he said. "We still argue about truth, still doubt what we know, still believe that the world can be understood." Outside, London hummed with the pulse of the modern age: trains, screens, satellites, storms. Inside, beneath the quiet hum of the lights, the legacy of 4 centuries endured. The tools had changed, but the vow had not. They were still there, the descendants of Newton and Hooke, Boyle and Darwin, guardians of a fragile light in an age that flickered between wonder and confusion, and as the sun dipped behind the skyline, its pale reflection caught the edge of the Royal Society's seal, a whisper of light on glass as if reminding them, and all who would listen, that the pursuit of truth was never meant to end, only to be renewed. London rests beneath a quiet sky, its lights shimmering across the Thames like scattered stars. The city hums with the rhythm of a world transformed, yet beneath its endless motion lies a memory, a small room in 1660, a handful of thinkers, and a single candle whose light has never gone out. From that flame began a journey that would shape the course of human understanding. They gathered not to worship power or crown, but to ask questions, to observe, to reason. In an age still bound by superstition, they dared to believe that the universe could be understood, that nature spoke a language the human mind could learn to read. That belief became a seed, and over centuries it grew into something greater than any of them could have imagined. One by one, generations carried the flame forward. Boyle and Hooke uncovered the hidden structures of air and life. Newton turned the movements of the heavens into the language of mathematics. Herschel looked deeper into the sky and found new worlds where none were known before. Darwin turned that same lens inward, showing that life itself was shaped by time and change. Rutherford revealed the heart of the atom, and Crick and Watson found the code that wrote every living thing. In the last century, Hawking lifted the same questions toward the edges of space and time, proving that even when the body is bound, the mind can travel beyond stars. Each of them became a link in a long and unbroken chain, each discovery not an ending, but a new beginning. The Royal Society endured through all of it, not as a monument of stone, but as an idea. It stood through wars, revolutions, and the rise and fall of empires, carrying forward the same promise, that knowledge, tested and shared, is the purest form of progress. Its motto, "Take nobody's word for it," was not rebellion, but trust in reason itself. To question was not to destroy belief, but to refine it. To measure and test was to honor creation by understanding it more deeply. Centuries passed, and the world those men once dreamed of became reality. Their instruments, once made of brass and glass, are now satellites and sensors orbiting far above the Earth. Their notes, once written in ink, now flow as data through invisible currents around the globe. What began in candlelight now glows in the blue light of a million screens. Yet the purpose remains the same: to see clearly, to understand truly, to move beyond fear into knowledge. Science has never been perfect, and neither has humanity. There have been errors, arrogance, and missteps, but always the same pattern returns. Curiosity falls, and then it rises again. The pursuit of truth bends but does not break. It survives because it is not built on one person, or one nation, or one moment in time. It lives because each generation chooses to keep asking, to keep wondering what lies beyond what is known. If the founders of that first fellowship could walk through London tonight, they would see their dream alive in ways beyond imagination. They would see laboratories where new medicines are born, observatories tracking galaxies they never knew existed, and universities where young minds still gather to question the world. They would find their beliefs still alive in classrooms, in experiments, in every act of curiosity that refuses to settle for ignorance. They would recognize the same courage they once had, the courage to doubt, to seek, to believe that reason can lift the human spirit higher than fear ever could. The story that began with a single candle in 1660 has traveled through centuries of discovery and struggle to arrive here, in a world illuminated by its legacy. From the first spark of inquiry to the orbit of satellites circling the Earth, the journey of science has been the story of humankind learning to see itself, to understand that we are not separate from nature, but a part of its unfolding design. The flame that once lit a small London room now shines across oceans and continents, passed from hand to hand, mind to mind. It is the proof of what we are capable of when we choose curiosity over comfort, knowledge over superstition, and reason over fear. It is the inheritance of every human being, the quiet triumph that outlasts empires and kings. From the candle to the atom, from the telescope to the computer, the same light endures. The light of understanding, fragile yet immortal. It has crossed centuries to remind us that knowledge is not only power, but compassion, not only discovery, but connection, not only progress, but memory. As night falls over the city and the river mirrors the stars above, that light continues its journey, moving silently through time. It asks us, as it once asked them, to keep looking, to keep learning, to keep the flame alive. For in the end, that is what defines us. Not what we conquer, not what we own, but what we strive to understand. From the candle in that small room in 1660 to the satellites now circling the planet, the path remains the same. Knowledge is the greatest inheritance humankind can leave behind, and the light of reason still burning after all these centuries is its eternal gift.